Time. So all we're going to do tonight is review stuff, because just looking at our timeline, today's Tuesday, tomorrow Wednesday we have the group presentation, and then Friday we have the exam. Question?
This is being recorded, right?
Yeah, I just started the recording. Of course, technology being what it is, it should work, but it said, what? Huh? Yes, it's...
Yeah, it's on moving.
Yeah. Okay, so we have studied the first two parts of the textbook. The parts having... Units 1 through 13 and 14 through, I don't know. We didn't cover all of the second part, and so we'll only cover what we have talked about in class. We won't cover other things. Sorry, trying to keep up with things. I still don't see Tioni or Eliezer.
What are we doing?
At work?
Yeah, he's volleyball game.
What happened?
He should be coming shortly, but he says he's going to be late.
Okay, so one thing that you know absolutely is going to be on the exam is a question about the scientific method. And you will need to first write down these 4 steps that are shown. Now, there are different variations you'll see of the scientific method. This is the one that I think is nice and useful. It's one of my big priorities for this class to make sure everybody understands the scientific method, because it's the basis of what science is about. As we learn things about astronomy, everything that we think we know about astronomy comes from following through this process. So you have those steps: observe something interesting, create a hypothesis that has these 3 parts. Number 1 explains why observation occurs, right? Your hypothesis needs to say, I saw this and it happened because of this. The reason needs to be based on scientific ideas. It has to be based on something that is a part of nature that has been studied before. So you're expanding something that was previously known. It's not coming up with something completely new out of nowhere. It's based on other ideas. And you remember my example of, noticing the ice cream tastes better in a certain location than another, and suggesting, well, maybe it had to do with the linkage between smell and taste. And then you come up with a test that could potentially prove it wrong. You can never potentially prove something right. Science can't prove things right. It runs tests, and if it passes the test, you say, okay, it passed in this aspect. If it fails, you know it fails. But if it passes, you would have to test an infinite number of different ways before you would know that it's right. And of course, infinity is not possible. So you do that test, and then finally, if it passes the test, you go and test a different prediction of the hypothesis. If it fails the test, then you go and modify the hypothesis. So this process is never actually completed. The scientific process is never done. We close the book. We can just keep going until we get a lot of confidence. So something as simple as gravity. You know, if I let go of this, it's going to fall, right? You know that. No question, I hope, in your mind that if I let go, it's going to fall. And yet, scientists would say it's a theory that it's going to fall due to gravity. It's not something that we have proven correct. So it's important to understand, what theories don't mean you don't have confidence, but you have higher and higher confidence as you go through more and more tests. Okay, so you will have to list those steps, and then I will give you a scenario. I will say, you observe that your hair grows longer during the summertime than during the wintertime. Now, I doubt that's a true observation. I'm just making up something. And then you're going to use that observation, and I'll try to give you a true observation instead of a bogus one, and use it as an example of the scientific process. So you would put step 1, I observed that my hair grows more during the summer than the winter, right? Because step 1 was the observation. So I give you an observation. you have to be on the ball enough to say, aha. So I just write that for step 1. For step 2, then, you have to create a hypothesis that follows those. So you have to say, okay, so, well, we know that vitamin D comes from sunlight and that vitamins can be beneficial to growth. So maybe hair, grows because of increased vitamin D during the summer when you have more sunlight. Right? Just coming up with something that's based on scientific ideas that could potentially explain why. Now, once again, I'm not saying that that's a correct hypothesis because I don't even think that my observation was correct. But then I would need to create a test. So I would have to suggest a test. So I might say, okay, well, I'm going to find a topical cream that I can rub on my head that's going to put more vitamin D there and measure hair growth on, 100 people with the cream and without the cream for a set period of time and see if the cream changes the rate at which the hair grows. And if the hair grows the same with or without the cream, then I'm wrong. But if the hair grows more with the cream, then I might be right. And so I would go through and say, okay, so if one of those two, if the hair growth is the same, then I'm going to have to go back and modify my hypothesis. If the hair grows more with the cream, then I'll go back and test it a different way. I don't have to say what my second test is going to be. If I do, you get into an infinite loop. Right, but you have to say, okay, so this outcome, I go there. This outcome, I go there. Any question about that part?
Nope.
Good. I mean, you know exactly what's coming. It's always disappointing when somebody, for instance, doesn't write the observation in the practical part, or things like that. Okay. So moving on. Oh, yes, and here is my standard ice cream application that I used in class before. You can read it. Obviously, it's on the notes. Looking at Unit 1. Unit 1, we had words like star, satellite, solar system, and astronomical unit. You need to know what those are. Who can tell me what a star is?
All the planets.
Sun in the northwest sun?
Okay, the sun is an example of the star. A star is something out there that is producing lots of light because of fusion going on in it. That's pretty much the key. If fusion is going on to produce the light, and it's a station, a standalone object as opposed to fusion occurring in a bomb on Earth, then it's a star. If there's no fusion, it's something else, like a planet or something else. Satellite. We think of satellites as only human-made satellites, but it's actually broader than that. Yeah. Satellite is something that's orbiting around something else. So the Earth has the natural satellite, the Moon. It has artificial satellites like the Hubble Space Telescope. There are actually other things that orbit the Earth besides the Moon that are really tiny. So satellites are things that orbit. And of course, according to Weekly World News, there's a kid born so fat that he had planets that were orbiting his body. And then they did a follow-up like a year later that life had evolved on the planets orbiting his body. Yeah, when you got a good one, you just can't go to the well too many times. Okay, solar system. What are the things in our solar system? You should know the things in our solar system. So what do we got? Holly.
Planets.
Do we need to know about the things in our solar system?
At this point, no. At this point, we just need to know what we have. So what were you saying?
Planets.
Okay, we have planets,
Sun,
the sun,
Sun.
moon,
asteroids.
asteroids.
We
Caleb?
have to know, like, every single planet in our solar
No, not at this point. You will later. That, huh?
That's the planets.
Yeah, we have 5 dwarf planets.
Comets.
Comets are, and I'll just go to the 2 things they come from, Oort cloud objects and Kuiper belt objects. Comets, same type of material. The difference in the Oort cloud and the Kuiper belt is basically where Pluto is. Pluto to Eris, all of that is the Kuiper belt. And it's in the plane that we're orbiting the sun. Yeah, a bunch of ice balls out there. And then you have the Oort cloud that is a spherical shell that's much further out. Question?
So if we basically just know what you have in parentheses, that will be good.
That's right.
Which is basically what's
Well, of course. We're only reviewing here. I'm not teaching anything new. And of course, with the solar system, we have different size scales we use. You know, we might measure the distance between atoms in units of nanometers and micrometers. But if we're going to measure the distance between, let's say, the Earth and the moon, what would be the most convenient unit to use there? Not yet. The kilometer. The kilometer would be the most convenient if you're talking about the distance from the Earth to the moon, because the moon's not that far away, a few thousand kilometers or so. But if you're talking about our next nearest neighbor or the planets orbiting the sun, then the most convenient unit is the astronomical unit. And what's the definition of the astronomical unit? The average distance between the Earth and the sun. It's a very simple definition, and at least every other year it comes up on the test question, so it's reasonably common, that just make sure you know what the astronomical unit is. Okay, then moving out beyond the solar system is within the Milky Way galaxy. And other things in the Milky Way galaxy, well, the nearest thing is Proxima Centauri. Proxima because near. The nearest thing you can see is Alpha and Beta Centauri. Alpha Centauri, I should have said Alpha Centauri A and Alpha Centauri B. So we have these star systems that probably have planets, just like our star has planet. We have we go farther away, we're going to start having clusters. You can have open clusters or globular clusters. We haven't learned about clusters very carefully at all. Go bigger, and we're part of the Milky Way galaxy, which is a big rotating disk. Go outside the Milky Way galaxy, we have the Andromeda galaxy, something we've been working when it's clear to help you understand where it's located. The Andromeda galaxy is another spiral galaxy like ours that's visible to the naked eye if you go somewhere where it's dark out. There are other types of galaxies. If you go in the southern hemisphere, you would see the large and small Magellanic clouds that, we say Magellan and his sailors discovered. Of course, that's kind of like the meme of Columbusing things, Surely Magellan and his sailors weren't the ones that discovered it. They were the first Europeans to see them. Because they're visible in the southern hemisphere. But those are different type of galaxies. They're irregular galaxies. They're not elliptical galaxies. They're not spiral galaxies. They're irregulars. Our galaxy is part of a cluster of galaxies called the local group. So the local group is a cluster of galaxies somewhere in the ballpark of 50 galaxies that are orbiting around each other. And I told you right now the Sagittarius dwarf galaxy is inside of our galaxy being torn apart. It's a small, it was a small dwarf elliptical, and now it's just a being torn apart galaxy, at least so I believe. You go bigger, you have superclusters. We're part of the Virgo cluster. You have the entire universe, which is made up of galaxies that appear to be on lines called filaments. If we're going to talk about big things like galaxies and the size of the universe, we have two additional units that become convenient. We have the light year. How do you define a light year? Homework question. How far light travels in 1 year. So a light year is a unit of distance. You also have the parsec, which we have not learned how to define yet. We haven't learned it, have we? No.
So what would be light year?
The distance that light travels in 1 year. What?
Light travels, like 399 something.
Well, basically 300 million meters
Yeah.
a second.
So then you times that times 60 and times.
Yeah, until you get out to a year.
That's a
Yeah.
pretty large number.
Yes, it's a very large number, yes. Okay, the Big Bang. The Big Bang is science's answer to where everything began. It comes from observing that everything is moving away from us and extrapolating back and saying, well, it must have all started together. Actually, a derisive term that Fred Hoyle came up with when he was talking about how ridiculous this idea is. And he said, well, where did it all start? Just with some big bang? And scientists said, yeah, about sums it up for me. And so that's where it got its name. Density is the mass per unit volume. That's how much mass is shoved in something. So you can think of like air is low density. There's not much mass in the air. You go in water, there's more material there. You can feel it pushing against your hand a lot more when you swing it in water than when you're in air. It's more dense. Obviously, your body is fairly dense. Your body's a solid, so you can't put your hand through it like you would water. You take something like iron, it's more dense. Of course, everybody knows that lead is really dense, right? But not as dense as gold, which is not as dense as osmium, which is the most dense of our material. You see osmium there, close to the center, element 76. Uranium is much, much more dense than lead as well. Hence, they will use depleted uranium in armaments because it's really dense, so you drop it, and it's really heavy and will go through things when it hits them. That's the reason to use the depleted uranium, because it's very dense.
So you said density is mass per unit?
Mass per unit volume.
Oh, volume.
Okay. The age of the universe, according to science, is 13.8 billion years old. Now, I told you right at the outset that you don't have to believe the answers of science. I'm not trying to indoctrinate you into a scientific worldview, but what I am trying to do is make sure that you understand what scientists believe and why they believe it. Holly.
So the study guide online said 13.7.
That would be based on the time when I made one document versus another. It was 13.72 plus or minus a small amount, and then 13.75. Now it's 13.82. Right? They keep refining the numbers. So I would not mark you off if you put 13.7 instead of 13.8. I mean, you know, what's 100 million years between friends? It's okay. Scientific notation, you should be able to convert numbers back and forth between scientific notation and regular notation. So remember things like, 5.13 times 10 to the 7. 10 to the 7 means a 1 followed by 7 zeros. So you accomplish that by just writing, move this over 7 times. That was 2, 3, 4, 5, 6, 7. Fill in my zeros.
Oh, that's how we need to write it.
Well, you don't have to write it that way, but that's how you convert it. You need to be able to convert numbers into and out of scientific notation. So if it was a plus, I was moving the decimal point to the right the number of times the number was. If it's a minus, I'm going to move it to the left. So if I had 5.13 times 10 to the minus 3, I'd write 5.13, and then I move it 1, 2, 3 to the left, to the left because it's a negative sign. So that's how you do scientific notation. And of course, if you can do it one way, you should be able to do it the other way. You just count those places you would have to move the decimal and put the times 10 raised to. Got a question?
Yeah, is there a point in between the 5 and the 3?
No, there's not. I started with one and then I moved it.
All right. Is that an acceptable answer then, instead of defining what scientific notation is, if I just did an example like that?
Well, on the test,
Yeah.
all of your questions except for the one that is on the scientific notation are going to be multiple choice or true and false.
Okay.
So you don't have to worry about did I write it incorrectly.
Yeah, I just was wondering if you define scientific notation, if I just gave an example like that.
That's a good.
Exactly.
Yeah, you won't have a question like that, so. Well, thank you. It saves me time. Right? Holly?
Will we have questions where we have to do calculations?
You will have questions that require calculations, yeah. It probably will be 3 or 4. out of a total of somewhere between 40 and 50 odd questions. So it's a small percentage of the questions that will be calculational. So you should bring a calculator. Remember, you will not be allowed to use your cell phone as your calculator.
Well, we have to memorize formulas.
No, but you do need to have memorized those prefixes, the centi, milli, kilo, and so on.
Prefixes?
Excuse me?
Yeah, you said something prefixes.
Yeah, the prefixes, the kili, centi, all those things, they're in the front cover of your textbook.
Yeah.
I think just the front cover is where they're located. Yeah.
Get them in Moodle?
Excuse me?
Would we get them in Moodle?
Well, they're in the cover of the textbook.
Yeah.
There.
They just-
Right. You got it?
Yeah, they're just right
Yeah.
there. Still in the textbooks in front.
Okay, let's get through some other things because I'm going really slow. I mean, this is a review, but we don't want to be here bored for 3 hours, according to Kendrick.
No.
That was not the plan. Okay, so we can cross things off. I've already talked about the scientific method, the hypothesis. Well, hypothesis, educated guess, right? Hypothesis, the goal is to try to be right, but you don't have enough knowledge to always be right. What's the difference in a hypothesis and a theory?
Theory is more science.
Yeah, a theory you've actually tested at least a little. You've got some reason to believe it's true instead of, well, I used some logic and came up with an idea. Laws,
They're basically been tested enough to be accepted as true.
that's part of it, but not the only part. Laws also need to be very broad in their application and usually something that you can write in a simple equation like Newton's laws of motion. Sum of forces equals mass times acceleration. It works everywhere and it's very simple to write in an equation. There's not a hard and fast rule, by the way, for, that's a law, not a theory.
Right.
It's kind of loose. A model. Who can give me an example of a model? Yeah, a scientific model, not, for instance, Paulina Porizkova. Okay, the celestial sphere is a model. Now, the celestial sphere, the ancient Greeks actually thought it was correct. We know it's not correct, but it gives us a framework, an easy way to think about the locations of the stars so that we can describe where they are. So it's a model. We don't believe it's correct. We don't pretend it's correct, but we still use it because it's useful in describing something. Universality simply means it works everywhere in the universe. We believe that the laws of physics are universal, that everywhere at all times in the universe, the same laws of physics have applied. If that's not true, most of what we believe about the Big Bang Theory would have to be not true as well. So, for instance, many creationists have focused on things like if the speed of light changes, like the speed of light today is not the same as what it was 1,000 years ago, then that changes everything in terms of the building up to the Big Bang Theory. And so you'll find people who write articles about has the speed of light changed, because if it has, then that breaks everything. So universality is the belief we have that the laws of physics have been the same everywhere at all times. Protons, neutrons, and electrons, where do you find these babies? Yes, in the atom. What things do you have in the center of the atom? You have the nucleons, because those are the things that are in the nucleus. And which two of those three are the nucleons? Proton and neutron. Where are the electrons found?
Orbiting.
Orbiting. In what shape?
All of them.
We don't really know. We don't know, right? When I was in high school, I thought that they were doing like circular orbits if they were in s orbitals, because
Doesn't it depend how much energy they have and what step they're at?
they're orbital, yes, but we still don't know what they're doing, right? So Whether it's an S orbital or P orbital, right? S orbital, we draw it as a sphere because it's most likely to be found in a spherical shell. A P orbital, we draw like this. We still can't say what the electron's doing in either case. All we can say is this, it's expected to be found somewhere in this spherically symmetric shape. This is expected to be somewhere in one of those lobes.
Wouldn't the orbit change on how far, how much energy is in there?
The distance where it's most likely to be found will change. The angles where it's most likely to be found will change. But that's just where it's most likely to be found. We still don't know what it's doing. Right, so that's what these shapes are. They're where we're likely to find it. But we're not telling us what it's doing. Okay, force. What is a force? Anything that blanks or blanks? Pushes or pulls. And if I want to put a force on this desk, what do I have to do?
Push or pull.
I have to push or pull it. So I have to contact it. Except Newton discovered that gravity is a non-contact force. So is electricity, so is magnetism. Those are forces that we can apply at a distance. Those are, conveniently enough, fundamental forces, whereas contact forces are actually the result of electromagnetic forces.
But couldn't you put a non-contact force on that to, like, breath blowing on it? I mean, it wouldn't move, obviously, but it would still be putting a force on it.
That would be... It would be contact. It's not contact between me and it, but it's something that that would be an example of the same thing as if I take a baseball and I throw it to you.
Yeah.
When you catch it, there'll be a force applied to you.
Yeah.
When I threw it, I put a force on it. And so the force was mediated by an intermediary. And actually, particle physics, that's how we treat all forces. All forces are the result of an intermediary like that. Yeah?
Do we have to do stuff like excitation, de-excitation?
We will get to that at the end, yes. That is something that is on this test.
Okay, one more question, like for you said
Didn't mean to do that.
Nuclei in the middle? Nucleons?
Nucleons are the things that are in the nucleus.
Okay.
Okay. This here, Unit 5, things in the sky. You should know where the horizon is. Remember horizontal. If you can remember the word horizontal, you know where the horizon is. Very tough. What about your zenith? Straight up, nadir. Straight down. Prime meridian. Okay, first we should start with what's a meridian?
They go from north to south.
Yeah, line that goes from north to south. The prime one?
One that goes through zenith.
Okay, no, the prime one is not the one that goes through your zenith. That's your personal meridian.
Didn't that go through England?
The prime meridian is the one that, it goes through Greenwich. Or yes, if we're Americans, it goes through Greenwich.
Oh, America.
Greenwich. Hey.
Is there any other reason that's the prime meridian?
No.
Okay.
Alina.
Do we have to, we go to tell them their position or to locate them where they are?
For these here,
So,
they're going to be more about knowing the definition. When we go out in the night sky, we'll be finding things like the equinoctial couloir. The equinoctial couloir is the thing in the sky that is equivalent to one of these things. Which one is it equivalent to? What is the equinoctial couloir equivalent to? I mean, that's what is it equivalent to for a thing on Earth?
Like what? Equator?
What do we use the prime meridian? See, I give you answers. On the test, I won't give you answers. On Earth, we use the prime meridian to measure the distance going along the equator or in that direction. In the sky, we use where the prime meridian is the reference point for 0. In the sky, we measure right ascension in the direction along the equator, and we have the 0 position for right ascension is the equinoctial couloir, which is the meridian that goes from the north celestial pole through the vernal equinox to the south celestial pole. By the way, what's happening tomorrow? Besides student presentation? autumnal equinox, which means we are starting which season?
Fall. Autumn.
Yes, autumn.
I thought it was 21st.
It varies by year, and I'm pretty sure that this year is the 23rd. It varies by year. It has a plus or minus a day or two on it. So, yeah, your thinking wasn't incorrect. It depends on the year, if it was correct or not. And, of course, what is today special besides my son having his finger surgery?
The night before.
No, it's Mom's birthday. Come on. Okay, so we've talked about your meridian. The ecliptic, the path the sun takes as observed from Earth. Now, that's using the celestial sphere model. What's really happening? What really defines the ecliptic? Yeah, our orbit around the sun. We have to be a little bit careful with the wording.
Oh, yeah.
Our orbit around the sun. When you say rotation, it means about an internal axis. So the ecliptic, we will describe it. We know that there is an incorrect idea in saying that's the path the sun takes as it goes around the Earth, because the sun isn't going around the Earth, but that's still what it appears to be. So it's correct if you say it's the path the sun appears to take going around the Earth. Equator, not the same as the ecliptic. What's the equator?
It's the line that goes around the center here.
Yes, it's the one that goes around the center of the Earth. So that one has to do with the Earth's rotation, whereas the ecliptic has to do with the Earth's orbit around the sun. And then we have the celestial equator, which is just taking the Earth's equator and throwing it out to the celestial sphere. Yeah.
I'm still kind of confused as to what the equinox is.
Okay, we talked about the prime meridian.
Yeah.
The prime meridian is where we measure 0 degrees for our longitudes. The equinoctial couloir is the same idea, but in the sky. It's where we measure 0 hours, minutes, and seconds right ascension.
Oh, okay.
And then the Earth's rotation, if you point up here and it's 0 right now, in 1 hour, I'm going to be pointing at 1 hour right ascension as the Earth rotates. And of course, the Earth is what's rotating, but when we're observing the sky, we tend to say, as the sky rotates from east to west, instead of as the Earth rotates from west toward east. Okay, latitude on Earth, that's measured north and south of the equator. In the sky, instead of measuring latitude, we measure the declination. The declination, the decline. The declination is 0 at the equator, and then it's north or south of the equator. So declination and latitude are virtually identical ideas, just one on Earth, one in the sky. Likewise, longitude and right ascension, virtually the same idea, except for we don't use degrees for the sky, we use hours, minutes, and seconds because of the Earth's rotation. What is a constellation in the sky?
It's an area.
It is an area. How many constellations do we have?
A lot?
We have 88 constellations. They're officially defined, official areas, and each constellation has a picture, although that picture might be triangulum, the triangle, or microscopium, the microscope, and good luck finding the microscope, right? So we have 88 constellations. What do we call the other pictures we see in the sky? Asterisms. Give me an example of an asterism. The Big Dipper, the Northern Cross.
Leo the Lion.
Leo is a constellation. The Summer Triangle. Orion's Belt. That's a constellation, yeah. What?
The white.
The white?
The one that's like the queen.
Oh, the Cassiopeia, that's a constellation.
Oh.
Ursa Major is a constellation, but within Ursa Major there is a very well-known asterism.
North Star.
Big Dipper. Ursa Minor, the small bear, is also a constellation, but it has a very well-known asterism. The Little Dipper, and the North Star is the end of the Little Dipper.
Asterism is part of a bigger constellation.
Asterism can cross over as well. And it's not the official picture that goes with the constellation.
Is Cassiopeia not also an asterism? Like, is it not
Correct.
asterism inside the constellation?
Now you could consider, I won't for your lab final, but you could consider, okay, if we think it's a W for Cassiopeia, we say the W is an asterism, but really that W is what we see for her.
Right.
And so it just counts as her and not as its own asterism. Okay, yeah, skip over those. Circumpolar. What are the circumpolar constellations? What's special about them? We focus on them a lot in lab, although you may not remember that that's what we're focusing on.
They never go outside.
Well, because we never go outside. Yes, I thought you were going to say because they never go out of sight. Circumpolar constellations are constellations that will never set. It depends on your location which constellations are circumpolar. But we look at those a lot because it doesn't matter if you go out early in the evening, late in the evening, in the fall, in the spring, they'll be visible. You just have to figure out where they are.
Orion, one of those?
No, Orion is not circumpolar. In fact, Orion, if we were to go out right now, Orion is below the horizon. As if we could see stars right now, but you know. So only the constellation, since we are about 40 degrees north of the equator, that means we're going to cut off 40 degrees worth of constellations. And so only constellations within, 50 degrees of the North Pole will be circumpolar. I think I did my math right. I hope so.
Leo lands only in spring, right?
Yeah, I believe Leo is not circumpolar.
Wait, so how do you calculate what one's a circumpolar?
Circumpolar ones are going to be constellations that never go below the horizon. And so I was speaking off the top of my head, but if we look at, here's the Earth, and so we are at an angle of 40 degrees north. And so as the Earth rotates around, we're going to see constellations that are falling in that region. And so since this is 40 degrees, this here is going to be 40 degrees. And so we're always going to see constellations that are within, it was 40, not 50. See, I should have paid attention. We're always going to see constellations that are within 40 degrees of the North Celestial Pole. If they're farther than that, they can set below the horizon. And likewise, we're never going to see constellations that are down in this region of the sky here.
Would we see those constellations all throughout the night, or?
Yeah, circumpolar, you're going to see them anytime at night, of course, in any time of the season.
Would that number be greater or less if you were at the equator?
If you were at the equator, then you would have no circumpolar constellations, because there's always going to be half the sky that you don't see. And it's going to go through so that you see all the sky in the course of a day. If you were at the North Pole, everything you see would be circumpolar.
Okay.
Yeah, question? Okay. Yeah.
So, example of a circumpolar, would that be like the Big Dipper?
Yes, the Big Dipper is circumpolar. And so all those ones up there, Big Dipper, Draco, Little Dipper, Cepheus, Cassiopeia, those are all circumpolar. Okay, diurnal motion, we didn't talk about much, but diurnal motion is the daily motion. The Earth is rotating. Did you have more to add, Caleb? No, okay.
What?
The daily motion.
That's what diurnal is.
Yeah. And notice here we have how we identify the positions. I've talked about it up above. We identify positions of stars using their, as you did in lab last week. What did the alpha stand for? Yes. And what did the delta stand for? Declination, right. So we use those to identify the positions of the stars. Just like the city of Lincoln, Nebraska has a specific latitude and longitude, the star Rigel has a specific right ascension and declination. And so if you know its right ascension and declination, you can look at a map of the sky and locate where it is. Okay, all the way up to Unit 6. We're halfway almost through the first part. Yeah, I know, oh my. Defining the calendars in years. A year is defined as the time that it takes for the Earth to do one orbit around the sun. How many rotations does the Earth do about its own axis in 1 year? That is how many sidereal days are in a year.
One year.
In 1 year, yeah.
Something ends in a 3, right?
What?
It starts with a 3.
3, it starts with 3. Yeah.
That's the number of mean solar days in a year. That's the number of noons you'll have in a year. But the sidereal day, the number of rotations, is always one more than the number of mean solar days.
365 and a quarter or something like that?
It's going to be 366.2422. It's one more than the number of solar days in a year. And the reason is because the Earth is orbiting and rotating at the same direction. So as it goes around, it's rotating the same direction, and it actually does one more rotation than the sun because it has to do more than one complete rotation to get back to noon again.
Could we say that? The 365 quarter.
Well, you should know that the number of solar days in a year is 365.2422. Now, do you have to know it's 0.2422? You need to know that it's a little less than 0.25. You won't have to know it's 2422. Just a little bit less than 0.25. Why is it important to know it's a little bit less than 0.25? Because we have our leap year system, where we have a leap year every 4 years, we add an extra day, right? Unless it's divisible by 100, then we skip it. Unless it's divisible by 400, then we put it back in. And so if you do your math, you had 365 plus 1/4 minus 1/100th plus 1/400th, right? That's what the leap year system does. Or in decimal form, 365 plus 0.25 minus 0.01 plus 0.0025. So that's equal to 365.2425. That's the number of days we have in a calendar year. And you can see that's pretty good. It's different by 3 in that 4th decimal place compared to the best known number. That's why we have the leap year system, and that's why you need to know that it's a little bit less than 365.25. Otherwise, we just have every 4 years you add a leap year at the end. And that's, of course, the difference in the Julian and the Gregorian calendars is because of the Julian calendar having 0.25, you slowly had a drift in the seasons. Okay, so we've got the year, equinoxes. We've talked about equinox today, tomorrow, yesterday, I believe tomorrow. When the ecliptic is crossing the equator. So there's a specific point where the ecliptic crosses the equator. Or when the sun is on the equator is another way of saying it. So it's a time, it's a location, it's defined by when the sun's crossing the equator. The Antarctic is the southern region, the Arctic is the northern region, that are defined as 23.5 degrees from the pole. Why 23.5 degrees? Because that's the demarcation where you will have the sun is never going to set for at least a 24-hour period at one point during the year, and will never rise for another 24-hour period during one point in the year. So that's how we define the Arctic and Antarctic. Similarly, we have the tropics. The Tropic of Cancer, the Tropic of Capricorn, 23.5 degrees north and south of the equator, because those are the regions where the sun is at its farthest north and south. So the Tropic of Cancer, the sun would be overhead 1 day a year. Tropic of Capricorn, the sun would be overhead 1 day of the year. Anywhere in between there, the region we call the tropics, you would have the sun pass overhead more than once a year. Simple definitions. And of course, that angle of 23.5 degrees is very important for defining that, and that. Okay, so we have the equinox. Equinox, when the sun is crossing the equator. What about solstice? Solstice, S-O-L-S-T-I-C-E.
Then when it's farthest.
The solstice is when the sun is farthest from the equator. So we have the summer solstice, which in the northern hemisphere is around June 21-ish, 22-ish. And that's when the sun is as far north as it goes. Now the sun goes as high as what angle? As high as 23.5 degrees. You should know that number. That number is not going to be given to you on the test. You should know it.
The sun is going.
It's right there, 23.5 degrees. In the green box. So that's the farthest the sun goes north or south, because that's the amount that the earth is tilted. And so on the summer solstice, the sun is 23.5 degrees north of the equator. But we're 40 degrees north of the equator. So that means it's still 16.5 degrees south of us. So even on the summer solstice, the sun is going to be 16.5 degrees south of us in the sky. It won't pass overhead here. But if we were down at the Tropic of Cancer, then it would be passing overhead. Okay, so that's the summer solstice. The winter solstice here in North America is December 21. And obviously the traditional start of the new year, January 1, December 21, December 25. They're all supposed to be the start of the new year. Just depends on your calendar. We had some other calendars we talked about. Calendars like the Chinese calendar that uses the lunar cycle. That is, a new year always starts with, I believe it's a new moon. And so their year varies in length following the lunar cycle. Now the lunar cycle, we have the synodic month, that's from new moon to new moon, is, 29.7 days? I always get the decimal wrong in these numbers for some reason. And then you have the sidereal month, which is like 27.5 days. So you have the sidereal month, the time for the moon to do one complete rotation. The synodic month, the time from new moon to new moon. Different times because the moon's going around the earth as the earth goes around the sun. And once again, just like the earth's rotation on its axis, the moon is going the same direction. So it has to do more than one rotation to go from new moon to new moon. How many months are there in the year? Good, good. So how many lunar cycles are in the year? Approximately.
A little more than 12. Some years have 13.
Yeah, it's a little more than 12 because you have 29.7 divided by 365.24. I'm going to, of course, invert that to get how many months are in a year instead of how much of a year is a month. So if I just divide those, and I know you can't see what I'm doing here, but I'm just doing the calculation. 365.24 divided by sine of 7. Excellent. Yes, it is reading my handwriting, and my handwriting is apparently not pristine. There we go. 12.3 months in a year. Whoops. A 13th month. And remember the whole blue moon thing, 2 different definitions of a blue moon, but basically if you have either 4 full moons in a quarter, then the third of those 4 is a blue moon. Or if you have a month with 2 full moons in it, then one of those is a blue moon. There are 2 different definitions. It's not hard and fast defined. Okay, we talked about sidereal day, daylight savings time. What's the point of daylight savings time? No.
Daylight savings time was started for World War factory.
Yeah, it's funny that when you read about it, most times people give Benjamin Franklin credit for daylight savings time, but apparently that's inaccurate. He was a proponent of it. The idea of daylight saving time is to adjust the clocks so if people get up at 8, go out to work, whatever, that they are going to have sunlight for about the same starting and ending times. The idea being you'll use less power because you won't be up before the light, and so you won't have to turn on lights when you get up type of thing. That's the idea behind it. It's necessary because, well, the sun rises and sets at different times in the year. That's due both to us being tilted and the Earth not doing a perfect circular orbit, it's doing elliptical orbit, which means that when we're farther away from the sun, we're going more slowly, and that's going to affect the length of a day. So those things come together to give us a variation, that equation of time. We looked at the analemma that looks something like this. Yeah, that's a perfect figure 8 almost. For once, when I'm trying to make it not perfect, it comes out looking pretty good. The analemma is there because of the tilt and the shifting on when noon occurs. So we have daylight savings time to try to keep things constant. And of course, in my world, we would have I saw this option for calendars that, there's lots of different calendars that have been used, and the one that I think is awesome is a calendar that has exactly 52 weeks in a year. And then instead of having leap days, you wait until you have enough to put in a leap week. And now just think about it. I'm a college professor. I'm here permanently. You guys are only here for 4 or 5 years, but all through grade school. That leap week would be proposed to come between December 31 and January 1. So what does that do every 4 years? Gives you an extra long Christmas break. It would be awesome. It would be great, yes. And then you could set your work calendar the same every darn year. You wouldn't have to go through and change it all. I made a spreadsheet that does it so I don't have to. But you wouldn't have to change it all because it would just be the same. School would always start on this date. School would always get out on this date. Wouldn't that be great? Yeah. And then, of course, I would go convoluted to make everybody confused. I would use 2 time zones. One that's your local time zone that actually changes if I go from there to there. So the sun is always going to pass overhead at noon. And then another one would be an absolute like Zulu, so you could make appointments, Zulu time if you're going to another city, but you always have lunch at 12 noon local time. That'd be great.
I think that'd be a little confusing.
Yeah, it'd be a little confusing. Okay, moving on with this. Apparent noon or local noon is going to be when the sun is on your meridian. Why is it not when the sun is overhead? Why is noon not when the sun is overhead?
Because you're not at the equator.
Yeah, we're not in the tropics, so we would never have noon if that was the definition. Okay, what is anti-meridian? What does anti mean? Before. Anti-meridian is before the meridian, before the sun has crossed your meridian. Post-meridian, after the meridian. And what comes between anti-meridian and post-meridian? Noon. And of course, if you go in the other way, you go from post-meridian to anti-meridian, then you would have midnight. We have leap seconds. Those are fragments of seconds that are put in at the end of December 31. Because the length of a year is actually not as constant as we'd like to pretend. You know, our 365.2422, right? It moves up and down just a little bit. That's an average. And so those leap seconds are put in there to adjust for the variation in the length of the year. Okay. By the way, when I said Zulu, Zulu means universal time. That's the time in Greenwich, England. Or, Caleb's not here. I guess I'll just go on. Okay, lunar cycles. You've had 2 questions on quizzes about the lunar cycle. You should know that the lunar cycle goes from new moon to what? I don't have them in order here.
Crescent.
It goes to a waxing crescent, then what? Then a first quarter. Where's first quarter? Yeah, there. So this is the first one. The second one is a waxing crescent. Third one is the first quarter. Then Seth. Then a waxing gibbous. Gibbous is probably on. Yeah, here we go. So then we have 4 there, waxing gibbous. Then 5th is going to be the full moon. And then we'll go to a waning gibbous, a third quarter. I'm not sure why I put them in such convoluted order. And then we have a waning crescent, and finally back to the new moon. So that's the order of our moons. Remember I taught you things like dog. If you look at the moon so that you're looking below straight above you, in other words, don't go like this to look at it. As long as you're able to stand and see it, you're going to be looking below 90 degrees. If the right-hand side is completed, then it's waxing. If the left-hand side is completed, then it's waning. So that's one way to use those. Another one is if you can see the moon at sunset, it must be waxing. If you can see the moon at sunrise, it must be waning. So things to know about the lunar cycle. What causes the whole lunar cycle? The moon is going around the earth, and it's the angle between the sun, the earth, and the moon. Remember, one side of the moon always faces the earth. We always see the same side of the moon, to within a really good approximation. There's a little bit of wiggle because it's not a perfectly circular orbit. So sometimes going a little faster, sometimes a little slower, so it appears to have a tiny bit of wiggle. But essentially, we always see the same side of the moon. The dark side of the moon is whatever side is not facing the sun at that moment. So the dark side of the moon is moving. And if we see all the dark side, it's a new moon. If we see all the side that's lit up by the sun, it's a full moon. And in between. Eclipses. We have eclipse seasons that occur when the moon is crossing over the ecliptic. To get a lunar eclipse, that is, the moon is eclipsed, the moon has to fall in the Earth's shadow. So you have to have a straight line, sun, Earth, moon, to get a lunar eclipse. Which means that it has to be a full moon anytime you have a lunar eclipse. A solar eclipse is when the shadow of the moon strikes the Earth. And so for a solar eclipse, you have to have a straight line, sun, moon, Earth. And so that's always going to be a new moon when you have a solar eclipse. And remember, we are only 2 years away from having our very own solar eclipse here in Lincoln, Nebraska. This is 2015, right? Okay. Making sure. So we'll have a lunar eclipse right here, which is pretty cool. Excuse me? A solar. Yeah. Lunars are boring. I know. Lunars are boring because, well, it just looks kind of like a new moon. You know, it went from full moon to new to looking like a new and then back to full. And you see it any time it's dark. So every time it's eclipse season, if you have a lunar eclipse and it's nighttime, which for most of the world it's going to be partially nighttime during the lunar eclipse, you see it. Solar eclipses are rare because it's a very small part of the Earth that the shadow strikes. And in fact, you have annular eclipses I misspelled eclipse there. Annular eclipses occur when the moon is a little farther away than normal, and the Earth is a little closer to the sun than normal. So the sun is slightly bigger in angular size than the moon. And so in annular eclipse, you see the sun with the center part blocked out, but you can see the edges. Or you can have a total eclipse where the moon is slightly bigger in angle than the sun, and it blocks the entire thing. Okay, just one more thing here. Umbra. Umbra is complete shadow. So if you're in the umbra of the moon's shadow, you're seeing the complete solar eclipse. Penumbra means right next to the umbra. So penumbra means you're in partial eclipse, you're in partial shadow. So when you have a penumbral eclipse, it's just partial. And so quite technically right here in Lincoln, Nebraska in 2 years, it'll be a penumbral eclipse for us. But if you go to like Nebraska City, it'll be a complete eclipse there. Okay, I've already actually talked about most of the things here. Let's talk about those two. Anno Domini. What does that mean? Not after. In the year of our Lord. So Anno Domini, that's the year that Christ was born, in theory, according to somebody's calculation. BC is before Christ. No Latin for that. So that is since 532 AD, what we've been using for numbering our years here in Western cultures. If you were to go to Japan, Japan still uses in the year of the emperor. So during like World War II era, it was the Showa era. And it's, I believe, still now the Heiwa era. And so they count the years like, you know, when I was in Japan, I was only like Heiwa 4. It was like his 4th year as emperor. That was Emperor Akihito. During World War II, it was Hirohito, of course. So different cultures still use different ways of numbering the years. But we do have the AD BC system is pretty universal now. Most people say, yes, it's this in our system or this in the world system. What's the new set of abbreviations that is becoming more popular? CE, standing for? Common Era. And what's the other one? BCE, before Common Era, which means BC. And the whole reason is to try to take Christ out of it, so I try not to use those for the most part, because I like to say Christ, you know. It makes me feel trying. Okay, Unit 10, doing some geometry. This small angle equation, you had to use that in a homework problem. So you should be able to use that. We measure the size of things by the angle in the sky they take up. And so we could take something like the moon, and if we know the distance the moon is away from us, well, don't have that, well, be the radius, I guess. It would be the radius for those things there. And if we have its linear size, we can relate those and find the angle it takes up in the sky. D is the distance away.
And the X is the radius?
That's a multiplication sign.
Oh, I'm sorry.
Yeah, well, no, it's no problem. So what we have is alpha is the angular size of the object. So the angular size divided by this 57.3 degrees and then multiplied by its distance away gives us how big the object actually is. That's the way this is arranged here. So the linear size is L. If you want to find the angular size, you would take that and just solve it for alpha. And so that's how you find alpha. Yeah. The 57.3 degrees is using a conversion factor going from radians, because there's 2 pi times the radius, radians in a circle, or the circumference is 2 pi times the radius. And so we have that 2 pi divided, 360 degrees divided by 2 pi is that 57.3. And so it's converting from radians into degrees. Okay, so basically for this one here, just be able to use that small angle approximation. I've talked a lot already about the Earth, Moon, Sun geometry, so I'm not going further on that here. The history is coming up in just a... I go too far. Now we get to some history. Planets. Planets, wandering stars. They're not stars, of course. But if you were an ancient person, you know, somebody who lived before the time of Christ, you didn't know the difference in a planet and a star. You could be an astronomy student and not know the difference. When I was my first year at PUC, I was on a trip out to the beach with some students, you know, club activity. And one student who was taking astronomy was, you know, talking about these, and, you know, and they're all, you know, all reflecting light, blah, 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 and got confused and thought the sun was reflecting light from who knows what, you know. The stars are producing light, the planets are reflecting light. But back in the day, before Christ, they didn't know that. They just knew these were things that we can see in the sky. And so the ones that appeared stationary, that is, most of them didn't move with respect to the others, those were the stars. And the ones that appeared to move with respect to other things were wanderers, and they gave them the Greek word for wanderer, planets. So that was the original definition of planet. And so trying to describe that planetary motion, we had people who came up with ideas like, well, the sun was the center of the universe, or the earth was the center of the universe. We had people who were proponents of both ideas. But the prevailing opinion was, we can't feel the earth move. We don't see signs of parallax, that is, we don't see signs of stars changing position with respect to other stars as we rotate. And so they said it must not be occurring. And so the earth must be the center of the universe. And then built up the system with, okay, so the planets, the wanderers, must be fixed on these spheres that are rotating around the earth, with little gears to get them a little bit shifted, because, you know, they sometimes go a little high and a little low. And so Aristotle is usually the one that's given credit for putting this whole system together. A very convoluted, complex system that had all of the stars going around, or all the planets, excuse me, going around the earth. But Aristotle's system had a very significant problem. It could not explain retrograde motion. Retrograde motion being, you look at these planets and they appear to move constantly one direction in the sky, and then all of a sudden they'll stop, and for a short period of time they'll go the other direction, and then start going the forward direction again. Now, we did a lab where we saw geometrically why the heliocentric model, the model with the planets orbiting the sun, explains that. But Ptolemy came up with a very complicated system where you had the big circle, and then you had the little circle, the epicycle. The deferent is the big circle, the epicycle is the little circle. And you had the planets moving on these little circles. So if the planet is here, it's going like that in the little circle, and this whole big circle is going like that, so it's going really fast in the normal direction. But if it is here, then the little circle is a little bit faster than the big circle, and it'll go backward for a period of time. And so Ptolemy was able to explain retrograde motion while he still had the Earth at the center of the universe. And it was virtually 2,000 years that people believed that was the truth. You know, we talk about the scientific method. The scientific method wasn't invented yet at that point. They basically said, is it a beautiful idea? And, you know, do we have reasons to believe it? If they did, they said, great, let's go with it. So for basically 2,000 years, the state of the art in science was that we had this going on. So if you were taking this class back then, I would have said, and that's what it is, to the best of our knowledge. And then I'd be all red in the face at this point and say, oh, I was wrong. It's what I thought. It made sense, but I was wrong. So we have the heliocentric model first proffered up, 300 years before the time of Christ, but not getting any real traction in the scientific world until Copernicus came along. Copernicus, as he was dying, started actually admitting that he was the one putting these publications out, saying that the sun was the center of the universe, or the center, that's what he thought at the time, and that the planets were doing perfectly circular orbits. Now, a problem with his model was, while it did explain retrograde motion, like you saw in the lab, it didn't actually predict the positions of the planets any better than the Ptolemaic model. And so scientists had to make a decision. And of course, when you make a decision, a big part of your decision tree is going to be Occam's razor. Occam's razor says if I have two explanations that are both equally good at answering the question, explaining why it happens, that the simpler one is probably the correct one, right? The one that has lots of complicating factors. Those complicating factors are going to be prone to having errors. So Copernicus' model, being far simpler than Ptolemy's, would have said if these two models were presented at the same time, we would all jump to Copernicus's. But for 2,000 years of believing Ptolemy's model, scientists weren't ready to jump over just because, hey, that's a simpler explanation. So Copernicus' model wasn't actually adopted by scientists. It wasn't until you had the work of Kepler, who came up with his law number 1, the planets are doing elliptical orbits with the sun at one of the focal points. Number 2, that the area swept out by a planet in time is constant, which has rubber meets the road outcome. Kepler's second law, when a planet is closer to the sun, it's going to be traveling faster. When a planet is farther from the sun, it's going to be traveling slower. And then Kepler's third law, that the period, the time it takes to orbit, squared for a planet equals the semi-major axis, the average distance from the sun, cubed. If you use years for time and astronomical units for distance. So when Kepler came up with those laws, those gave dead-on predictions of where the planets would be. Now scientists had a model with better predictions, and they moved over to the new model. Now in between, we had a couple names I didn't mention. Galileo Galilei and Tycho Brahe. Galileo is very important to astronomy because, well, number 1, he improved the telescope that was invented in the Netherlands to observe the sky and to make systematic observations. And he saw things like the moons going around Jupiter, suggesting that unlike the model that had been developed, that everything out there is perfect and hell is below us and the earth has sin and so it's not perfect, that we could have things out there that, something was going around something out there, not just going around Earth, because we had moons going around Jupiter. And he saw sunspots on the sun, indicating the sun wasn't perfect. And so he saw a number of things. He saw phases for Venus and for Mercury, and those phases indicated that while they went through entire phase cycles, that couldn't happen with the Ptolemaic model. So his observations told us that that couldn't be right. He wrote his book, he belittled the Pope, he was forced to recant. Tycho Brahe, he had found the new star, Tycho's nova. A new star was blasphemous. How could you have a perfect sky and then have something new occur? Either it's now no longer perfect, like you have a perfect complexion, you get a zit, now no longer perfect. Or it wasn't perfect before and this made it perfect. And so that was a big problem and got a lot of attention. Because of that, he got this great observatory. He took really good measurements of where stars and planets were. Didn't come up with anything very useful for that, but he passed this data off to Kepler, who did use it. Going from Kepler, we get to Newton. Isaac Newton, pretty much the father of our modern physics, not modern physics, but classical physics. He did a lot of really important work in physics because they had the Black Plague. And, what else are you going to do during the Black Plague except for physics? And so he came up with his laws of motion. He invented calculus. He came up with the law of universal gravitation. Also, he could describe how things work. And his law of universal gravitation is the most important thing for us in astronomy because it explains why we have Kepler's laws. So, for instance, here we have Kepler's third law written out in equation form. Well, with Newton's laws of physics that he came up with, you can derive this equation and actually find that it depends on mass. So if we had something orbiting, let's say, the Earth instead of orbiting the Sun, you would have a similar relationship except for you would have a constant factor difference because of the mass of the Earth instead of the mass of the Sun. And so Newton's work gave us reasons for Kepler's to be correct. Things here in the vocab that I might have forgotten to say. The Galilean satellites are the 4 major moons of Jupiter. Foci, you have 2 focal points in ellipse. That's what they are. The minor axis, you have an ellipse. The minor axis is that direction. The major axis is the long one. The 2 focal points are on the major axis. Sunspots or storms in the sun, we'll learn about those later. I think we're good with those. So let's move on. I've already covered all of 13, all of 12. 13, we have a few more words here. Altitude and azimuth is an alternate way of identifying locations in the sky. I never talked about that in class, so you won't be tested on that. Evening star and morning star. Evening star and morning star are actually terms used for usually Venus. Venus, obviously not a star, but the first star you see in the evening or the last star you see in the morning is usually not a star, it's usually Venus. Why? Venus doesn't have a very large elongation. It's only like 45 degrees is the farthest we ever see it away from the sun. And so it's usually close to the horizon when the sun rises or sets, and it's very bright, hence that term. Okay, then we have a big set of physics units here. We had terms like inertia. Inertia is the propensity to stay in constant motion. So if I am running down the path, inertia is my propensity to just keep going the same speed, the same direction. And if Kendrick was so foolish as to stand in my way, he would have to apply a force on me to change my inertia, to change my motion. And so Newton's first law says just that. That an object will keep traveling with the same velocity, that is the same speed and direction, unless there's a force that acts on it to make it change. Newton's second law goes further and says that the acceleration, which is the rate at which velocity changes, the rate at which the speed or direction changes, is equal to the net force divided by mass. That is this equation right here. And then Newton's third law says for every action is equal opposite reaction. Or simply put, if I push on something, it pushes back with exactly the same force, exactly the opposite direction. Now, I was just reading the latest Jack Reacher book, and it uses a headbutt. Headbutts are always good examples here. If I take Dylan and I slam my head into his head, whose head hits harder? No. Newton's third law says it's going to be the same. The force my head puts on his is the same as the force his head puts on mine. So the first thing to think about that is, if I take the hardest part of my head and hit it on the hardest part of his head, we're both just going to be hurt. It's really kind of stupid. Now, there are things like, if I initiate it, I can tighten up all my muscles and make sure my head doesn't snap, and hope that his head snaps, so he'll cling and gets more damage from his brain bouncing around than I do. But really, if you're going to headbutt, it's going to be the same force. You need to hit something softer so that you're hitting something that will break before your head breaks. So if you're going to headbutt something, which I don't recommend, you would want to do something like headbutt the person in the nose with the crown of your head. Because you headbutt them in the nose, that's softer. It's going to break. The crown of your head won't. It's still going to be the same force on either one. And let's face it, those hard bones in here are probably going to tear up your head. But you won't be hurt as bad as they will be hurt. Even better, don't headbutt people. Yeah, I know. It's pretty sound advice, especially coming from a pacifist, you know. Okay, then we have Newton's law of gravity. His law of gravity, it's really important. We should all know our equation. Force of gravity is equal to G, mass 1, mass 2, over the separation squared. Now, you're going to be given that equation. You don't have to have it memorized. But you should be able to interpret how it works. You know, what happens if you double the mass of one object? What happens if you double the masses of both objects? What happens if you cut the separation in half? You should be able to go through those and determine what change that's going to have on the gravitational force. Because it's really important. Things like gravity gets stronger when things are closer together. When we talk about how stars are formed initially with a big cloud of gas. And then you have a shock wave that goes through that makes the gas molecules get closer together. When they get closer together, the force of gravity gets stronger and makes them continue pulling together until they form a star. And so the way that equation works with distance is very important to understand some basic things about how we get our universe the way it is. We didn't actually talk about the center mass. This is called an inverse square law just because that is 1 over distance squared. That's what inverse square law means. So the term inverse square law itself isn't important to us. It's being able to figure out how that works with the distance. The surface gravity, that's the gravity I feel here standing on the surface of the Earth. We tend to just call the acceleration of gravity G, but it actually just comes from taking these here, say, okay, that's the mass of the Earth and that's the radius of the Earth for the distance. That's how we calculate the surface gravity. It's just the things that I have in that circle. I've got to remember to scroll down instead of going to the next slide. Okay, going back to Newton, there's the law of universal gravitation, the definition of surface gravity here. Two things from the previous slide. And so you see G is capital G, lowercase g, the acceleration of gravity, capital G, that gravitational constant, times the mass of the Earth over the radius of the Earth squared. This equation here is the one I talked about using Newton's laws. You can derive Kepler's laws. And this here is Kepler's third law, except taking into account the mass of the two things orbiting. This is really important because we use this to find things like, well, what's the mass of a star? Let's find something orbiting it. If we can find the period and the distance between them, then we can calculate the total mass. And if the two are very different mass, like a planet and star, then we're just basically going to have the mass of the star, because the mass of the planet's tiny compared to the mass of the star. So this is an important equation for allowing us to find the mass of stars. Escape velocities and circular velocities. It turns out that using Newton's laws, you can define that if something's going to do a circular orbit, you have to have the specific speed of the square root of gravitational constant g times m. Remember that m is the mass of what you're orbiting. So if we're talking about the moon orbiting the Earth, this m would be the mass of the Earth. If we're talking about the Earth orbiting the sun, it'd be the mass of the sun. Divided by r, which is the separation between the two objects. So you have a different escape velocity or circular velocity depending on how far away and what mass you're orbiting. Which means that it turns out there is only one position, one radius away from the Earth, where for a circular orbit, you will have objects traveling 1 day to do an orbit. And so we call those geosynchronous orbits over the equator that are very, very important for communications, because then you can have a dish that doesn't have to change its positioning during the day. Escape velocity is how fast something has to be traveling to get away from a planet or from an object. And that escape velocity is very important for things like us having air to breathe. The escape velocity for Earth, that is using the radius of the Earth and the mass of the Earth there, is faster than the speed of oxygen and nitrogen molecules in our atmosphere, which means the Earth can hold on to nitrogen and oxygen in the atmosphere, giving us something to breathe. On Mars, Mars can't hold on to nitrogen and oxygen in the atmosphere. Very, very thin atmosphere that we couldn't live in. Even if Mars had 100% atmosphere, it's super, super thin because it's lost so much, and we couldn't live there. Venus' atmosphere is very thick because, well, it has a lot of gas, and like us, it can hold on to it. We spent a lot of time talking about tides. You need to know the difference in a high tide and a low tide, what causes it, the geometry between the Earth and the Moon and the Sun for causing the highest high tides, for causing the lowest high tides. The highest of high tides are called spring tides. The lowest of high tides, that means you have the smallest tidal difference, is called the neap tide. So we need to understand these things, what causes them, how they occur. There are some interesting things like tidal friction. Tidal friction means that we have something that's slowing down. What's actually happening is the gravitational pull of the moon causes a high tide, but the Earth's rotation causes the water to rotate ahead of the moon. And with that water rotating ahead of the moon, it pulls the moon forward. And so we're pulling the moon forward, giving it energy. Because the moon is getting energy, it's slowly moving away from us at about 1/4 of an inch a year. And so it's very interesting, that exchange of energy. Of course, if we're losing energy, we're giving it to the moon, we're slowing down. Remember, we learned that energy was ability to do work, and kinetic energy is ability to do work because of motion. The Earth is rotating, it has kinetic energy in that. We're losing it, giving it to the moon, so we're slowing down. So in this process of giving energy to the moon and making it go farther from us, we're also slowing down the Earth, which means we're making days slightly longer over time. Very, very slightly. Okay, we're getting down to the end, thank goodness. We won't go 3 hours. All right, getting to energy. Energy, the ability to do work. 2 ways we talked about it: ability to do work because of motion, or ability to do work because of configuration or position. So if I'm running, I could run, hit the wall, and do some work on that wall potentially. I don't want to. Because I'm moving. I could also have energy from position. For instance, I could take a bowling ball, and if I connect the bowling ball to that and pull it back here and let go, it's going to come swinging down. And so if I put a person here and let that bowling ball come swinging down and hit them, it would hurt. Now, when it hit them and hurt them, it would do some work on them because it's moving. But why is it moving? Because it started with a position up here. It had potential energy based on its position up here, converted it into kinetic energy as it swung. So we have those 2 types of energy: kinetic energy and potential energy. Now, with kinetic energy, if we're talking about atoms or molecules, there's so many of them, we can't talk about each one's kinetic energy. Instead, we just combine them all together and do statistics. We do calculations on statistics. And so that statistical calculation comes up with temperature. So temperature is a measurement that actually tells us about how fast the molecules are moving. The temperature tells us, being strictly correct, about the average kinetic energy of the molecules, the average energy in motion they have. So the higher the temperature, the higher the energy in motion that they have. Thermal energy is the name we give to the energy that they have because of their motion. So thermal energy, if you think about it, it's actually kinetic energy. But it's the kinetic energy of an uncountable number of molecules moving around. And so we just combine it into this one blob we call thermal energy. Now, something you probably have thought about at some level. If I touch this desk and it feels cold, why does it feel cold? Okay? It feels cold because thermal energy went out of my body into it. And thermal energy will flow from the hotter thing to the colder thing. So I touch it, if thermal energy flows out, it feels cold. If thermal energy flows in, it feels hot. That's how we have that sensation. And you may or may not have noticed things like you go to the beach, and if you have a black asphalt and a white concrete, the black asphalt feels a lot hotter. It's because it actually is. Because it's black, it's absorbing a lot more radiation and getting hotter. But then you have things like, you have a dock, and the dock is made out of wood. And you can walk on that wood and it just feels fine and dandy. But if you step on the flat head of a nail, it will burn you. It's the same temperature. The wood and that nail are the same temperature. Why does one burn you and one feels fine? The reason, obviously this isn't a physics class, so I'm going to go through this quickly. The reason is because that nail will transport heat very quickly. So it's hot, you touch it, heat flows into you, and heat from below flows up, and it just keeps coming. Whereas the wood, it's very bad at transferring thermal energy. And so you put your foot on the wood, you have like a flash of thermal energy that comes in so quick you don't feel it. And then the wood you're touching is your body temperature, and it stops. And it takes a very long time for heat to flow up from below so it doesn't feel hot. In case you ever wondered about these things, or the difference in what a carpet feels like versus a tile floor. Same temperature, one of them feels cold, one doesn't. It's the same idea. Okay, the unit of energy is the joule. So when you did energy problems, you had to use the units of joules. 1 joule is 1 kilogram times a meter per second squared. Kilogram is mass, measurement of how much stuff is present. Meter, distance, second, time. Put that all together and you get the joule. Force, on the other hand, we're not in force anymore, but force had units of newtons. 1 newton is, joule is meter squared. I said that wrong. I wrote the newton. A newton is a kilogram meter per second squared. A joule is a kilogram meter squared per second squared. So their units are quite similar. They're related, of course. Okay, now we're getting down to the end. Light. Light can come 2 different ways. We can have incandescence, giving off light because something is hot. We can have emission spectra, giving off light because electrons are falling from one energy level to another energy level in an atom or in a molecule. So we have these 2 different sources of light. If you see a continuous range of colors, that's the continuous spectrum. Continuous. Surprising. Coming off because it's hot. How do we determine the peak wavelength for the continuous spectrum? It requires you to go back to yesterday. It's of course going to be on the next page. I don't remember the exponent. Is it 6? The peak wavelength is, I think that's right, 2.9 times 10 to the 6 nanometers times Kelvin divided by temperature. Temperature. What units do we use for temperature? Have to use kelvins here. So we have the different temperature scales. We've got to use kelvins when we're using this equation. This is called Wien's law, and it's an important law to help us determine temperature for something when it's hot, looking at spectrum. So we look at you. You're giving off radiation because you are hot. But your body temperature is only around, let's say, 300 kelvins. So since your body temperature is only around 300 kelvins, that means your peak wavelength is going to be around, what would that be? 1,000 nanometers. Is that right? 2.9 times 10 to the 6. Oh, no, 10,000. Your peak wavelength will be around 10,000 nanometers. That's in the infrared range. Our eyes can't see infrared. So I can't see you guys in the dark because you're giving off radiation, but it's not in the visible range. On the other hand, the sun, it has a temperature of about 5,800 kelvins. And so the sun's peak radiation is in the ballpark of 500 nanometers. That's like in the greenish range. Sun look green? No, I would say it doesn't. Why doesn't it look green if its peak radiation is in the green? Because it has a fair amount of red, green, and blue. We have those three cones, red, green, and blue. And so the sun really is kind of white. It looks yellow to us because we have the atmosphere that scatters away the blue. Hence, we look away from the sun and we see the blue light scattered by the atmosphere. We look at the sun, we're seeing the sun minus some of its blue, so it looks yellow. Okay, so we have the emission spectrum, electrons falling from higher energy levels to lower energy levels. This is where it comes in, Tiani. We have the absorption spectrum, which is exactly the opposite. Absorption spectrum is when you have an atom in a lower energy level, photon comes along with just the right energy to kick the atom or the electron up to a higher energy level, and the photon disappears. So absorption spectrum, light comes in, it's absorbed, raises the energy of the electrons. Emission spectrum, electrons were already up in the higher energy state. They fell back down and gave off light. And for a given atom, since those are both set by the energy levels or the gaps between them to be more precise, you have exactly the same emission spectrum as you have absorption spectrum. That's the same colors appear in both. So they occur because of electronic transitions, absorption and emission spectra. Orbitals are the term we give for the state that the electron is in. So we have s orbitals, p orbitals, 3s, 2p, whatever. Those are the states, the energy states of the electrons. The wave-particle duality is that we can treat a wave or a particle as a wave or a wave as a particle. So we can treat light as both a wave and a particle, not at the same time, but it has a wave nature and a particle nature. With the wave nature, we're going to define a wavelength, lambda. We'll define a frequency, f. With the particle nature, we'll define an energy, E. But that particle energy relates to the wavelength or frequency. E is equal to hf, where h is Planck's constant and f is the frequency. Remember, our textbook uses nu, so our textbook says h nu. I don't like to use the nu because it looks like a V. I made that mistake in class. So we have the two natures, the wave nature and the particle nature. When we're talking about absorption and emission, we're fundamentally talking about the particle nature because we're talking about a photon coming off with energy equal to the gap. But then I drew it as a wave, and we measure the light as having a certain wavelength and a certain frequency. So we very easily move back and forth between the two ideas. And I hope when we get to heaven, God will teach me what the true nature of light is so I don't have to deal with this having two natures idea. Yes, a duality. I do not deal well with dualities. The word quantize is important. Quantize means you only have certain specific levels. So the energy levels in an atom are quantized. Remember, I went through the models of the atom, and we started with non-quantized models and then got to quantized. So the non-quantized models, we started with the plum pudding model, and then we went to the planetary model. Neither of those were quantized. Oh, that's beautiful. I didn't do it. But then Bohr suggested a quantized model where we had only specific angular momenta. Remember, we had angular momentum. Seth came up and did the little demonstration sit and spin thing so we could see the angular momentum. And from there, we have our standard model where it turns out lots of things are quantized in atoms. The electromagnetic spectrum is the entire range of waves that are carried by electric and magnetic fields. The connection between light and electromagnetic waves was made by a dude named James Clerk Maxwell. His family name had been Clerk, but his father adopted the name Maxwell. So that's why it's Clerk Maxwell. He looked at some laws of physics and determined that they predicted you could make a wave with electricity and magnetism. And the predicted speed was the speed of light. And he said, I just found a predicted wave that has the same speed as light, so they must be the same. That's kind of like me saying, wow, my car will drive 5 miles an hour, and Labyrinth runs 5 miles an hour. Hence, Labyrinth must be a car. That's about the quality of the logic that I see in what he said. But it turned out he was right. So light is just part of the electromagnetic spectrum. So you need to know the different parts of the spectrum. Having your radio waves, your microwaves, your infrared, your visible, your ultraviolet, X-rays, gamma rays. Okay. So he's on, yes, I'm going to be covering something that's appropriate. All right. So you should pay attention tomorrow when he's talking about the spectrum, because it's something you need to know about. In astronomy, we use lots of different parts of the spectrum, not just the visible. Now, it turns out there's only 2 parts of the spectrum we can see from Earth very well. The visible, fortunately, I believe God created us so we could see the stars. And then there is a radio window where we can see as well. So we have telescopes and the radio we can use from Earth. Okay, getting almost done here. Yeah, there's Wien's law. I thought it was up higher. Anybody remember what the name of this second law is? It's, we have Stefan and Boltzmann's names attached to it. This one here, the second one, says the luminosity, the amount of light that's given off, is proportional to the temperature to the 4th power. So you make something twice as hot, it gives off 16 times more light. And we saw that illustrated when I had the lamp out here and I made it brighter and dimmer. I made it hotter and cooler. As it got hotter, you saw the colors changing and you saw the brightness increase. Now, looking at the other pieces of this, that there is just a constant. This little script E is the emissivity. That's how efficient something is at absorbing or emitting radiation. We call these things that give off light because they're hot black bodies, because black is the most efficient color. A black thing will absorb a lot of light. You know that. You go on a sunny day and you wear a black jersey, like the Raiders did this last week. You bake. They still won. It doesn't happen every day.
Why did they keep the black jersey?
Because you have to choose the color beforehand. You can't wait till like the day before the game to choose your color. And so you look at general weather trends. The Denver Broncos did cheat on that one time. They got away with it. They just brought the wrong jerseys intentionally because they knew it was going to be hot in San Diego, even though San Diego said, we're going to wear our light-colored jerseys. The home team gets to choose. Denver brought only their light-colored jerseys and forced San Diego to wear their dark jerseys. And the NFL didn't even punish them.
Oh, wow.
Anyway, that's not important to this class. So the emissivity is the name for that. Remember, human bodies have an emissivity of like 0.97. We're pretty efficient. Stars likewise have an emissivity that's close to 1, which is perfect efficiency. And so for our textbook, it just drops that out and says, let's assume it's 1. The A is the area of the object. A bigger object obviously gives off more light than a smaller object. Bigger stars will give off more light because they have more surface area. Okay. Incandescence is the name for giving off light because it's hot. Okay. And I think, this is where I ended right here. We talked about the spectra and how we calculate the energies for the hydrogen atom. So that's where I stopped with my lecture. So that's where we will stop with our material on the test. So I've gone over in very quick fashion, clearly not encyclopedic, clearly not covering everything that's going to be on the test, but give you the range of things to think about for the test. Any questions before we pack it in? Yes, Alina.
Do we have to solve a problem like this?
You will have to work out calculational problems, maybe around 4 calculational problems. What they're going to be, I don't know at this point. I haven't even made it yet. But I won't put in 20 calculational problems. It'll be a small number.
How long are we gonna have for the test?
You'll have an hour. Usually people finish in less than a half hour.
Yeah, normal people.
I think
Yeah,
like
normal,
I
smart
think
people.
I think there's gonna be a lot of essays.
No, the only written part will be the part with
Yeah,
the
first one, theory.
scientific method. It'll actually be the last one on the test, but the one we talked about first tonight.
So it's multiple choice.
Huh? They're all multiple choice or true and false, except for that one.
Okay.
We should talk about physics and football sometime.
What was that?
We should talk about physics and football sometime.
Yes, but probably not in this class. What were you gonna say, Kendrick?
Do we have to manually look up all these vocabulary, or is there like a sheet on Moodle posted that has?
Well, there's this sheet, but of course it doesn't.
Yeah, I already have that.
You have the glossary in the back of your book.
Well, I know that. That's what I'm saying. I can go look up there.
Yeah, look
Okay.
all that one.
I didn't know if you already had it.
No, I don't have one where
That's fine.
we could.
No problem.
Yeah.
I just didn't.
Anything else?
Here we go.
Okay, we can go.
Basically, we can, that's on Moodle.
Yeah. And I will be uploading to, come on.
So every single of those vocabularies will be on the test.
No. Not every single one of the vocabulary things will be on. Oh my goodness, I don't know what's going on.
Thank you so much. That was a lot.
I gotta stop the recording here. Maybe. This is going super, super fast. Kendrick, I can't stop the recording, which does not bode well for me being able to post the recording.
So everything that's written up there will be, well, on the quiz, on the test, or influence the test?
No. These are just looking over major topics we've covered.
And what will be the topics that will be covered in the exam?
It will be a selection from this and the things that are in between.
Is this a PDF online?
Yeah, it's on Moodle already.
Well, no, I was just wondering if I could print it out.
Yeah.
You can print it out. Yay.
So what's the name of the link in Moodle?
It's like exam 1 review, I think.
Alright, there's many things in the Moodle page, well, astronomy page, lots of things.